Hello and welcome. My name is Cuneyt and I'm a software engineer from Turkey. I'd like to thank to Neo4j team for providing us with this opportunity to talk with you and present these topics with you. I'd like to talk about my project, Semantic Space, in this talk, which utilizes Dbpedia and Wikidata semantic web sources for enhancing knowledge browsing experience in web. So let me make this full screen first. I'd like to make it full screen. I have been working as a software engineer in Turkey for 10 years now, and my main expertise is in Java technologies. During my first years of my professional career, I developed an enthusiasm for semantic web and its uses in web and other areas. And so the idea of semantic space arises from a need to store knowledge in a structured way in a web application. Basically, I want to store articles and entities in my web page so that I could retrieve them later on. And I think it was useful because of the way we access knowledge is so unstructured, and when we read some articles or some books, we generally encounter many entities, many terms, topics, and it would be a good way to save these in a structured application and also see and exploit the relationships among them. So with my interest in semantic web and ontologies, I developed the idea to store these entities in a web application and exploit the graph relationships between those entities. Basically, the idea arises from this thought, and I will talk about how I implemented this web application with the use of my Neo4j database. And I imported Wikidata and Dbpedia. These semantic web data providers to my Neo4j database, and I think it's a good use case for Neo4j and a good data sources for knowledge graphs. So I will talk first about semantic web, and I will then present you a view of my application, and then I will talk about how I import data into my Neo4j database and how I approach to the design of the scheme of data in my Neo4j database. So there are some challenges, as you know, to designing schemes, and I will try to address them. So semantic web is a a term coined by Tim Berners-Lee in early 2000s, and it denotes the structure of data in triples, and as denoted as graphs. So in a semantic web data ontology, every data consists of a subject, a relationship, and a target entity. So this is very similar to how we store data in our knowledge graphs in Neo4j. And so this data provides many structured knowledge into our applications. And for example, when we try to search about an art painting about Paul Klee, we can search by denoting some properties relating to it, such as watercolor paintings. And so that when we search it through this denotion, we can retrieve watercolor paintings, and by simply searching our properties of those painting objects. Linked data refers to these data resources such as Dbpedia and Wikidata, but there are many others in web. There are many data sources and ontologies such as in healthcare domain. And earlier this day, another presenter talked about an earthquake ontology, which he used with his Neo4j database. And I think many of you already know about Wikidata and Dbpedia. And my application basically, as I told earlier, brings a memory to users. And another feature, because I have a structured data, I implemented a semantic search over this application. So with this, as I talked about Paul Klee and retrieving watercolor paintings of Paul Klee or another artist, by exploiting the RDF knowledge, RDF properties, we can retrieve quickly enough semantic queries and respond to semantic queries. Also, there are graph visualizations so that we might see the relationships between our entities. So we have some entities saved in our memory, such as in under certain topic, we have Barack Obama, and another topic, University of Wisconsin. I'm not sure if he has graduated from University of Wisconsin, but let's assume that. So when we have these two separate entities, the app will notify us that Barack Obama is graduated from University of Wisconsin. So the idea is basically to exploit these relationships to inform the users about this new knowledge. So the app looks like this. This is the graph page, and this is a graph visualization, and also this is the semantic search page that we talked about. This is the memory page where we have topics, categories, topics that you can see on the left. The space is the topic on topmost corner, top leftmost corner. And under this project vehicle are categories, and on top there are subcategories. So three levels of topics or categories are possible. So the main purpose is to organize this data. So I made a three-level category structure. So basically, we can see what entities we've saved in our application. So these are these may be useful in our future research and future learning procedure, so that we can remember what we've been studying about. And this is also another graph visualizations. Under space category, we can see how these different entities are interconnected with each other. So in the technical part, I'd like to talk how I imported the data, and then I will talk about how I designed the scheme of data, and then I will delve into how I designed in a fair and robust manner the scheme to retrieve data from the database, and I will give examples of two queries. So I used a tool PyIngest for importing this data from Dbpedia and Wikidata to my database. And there are in total 20 million nodes and 1 billion relationships in the database. And in these data sources, this number of entities and relationships exist. So as we mentioned earlier also, semantic data is held in triples, which are called RTF triples. So Joe Biden, he is not the president anymore, but Joe Biden is president of United States of America is basically a row. And there are thousands or millions of rows like this in an old file, which defines an ontology. And we retrieve semantic data in this format. There are other formats as well. But basically, the idea is to store each record in a row in triples. So by accessing a row, we can assign to relevant part of our database schema the values obtained from external data sources. This structured data also have some unstructured to it. So we have to have a method to import this data in our Neo4j database. So when we think about how we design our database, we need to consider some facts about databases. And I think the main concern when designing a schema is to decide and experiment how we retrieve this data. Because in the end, what we'll do is to retrieve the data. We store it because we want to retrieve it. And we want it to be as performant as possible and as easy as possible. And we don't want to write complex queries, and we don't want to have slow queries. So I considered this and based my approach on this when designing my database. So this is a small part of my database diagram. Basically, we have an entity, we have properties we obtained from Wikidata and Dbpedia. We have users. When users save entities, they are saved into user entity, and those user entity are connected to topic category or subcategory accordingly to users' actions. So first of all, I'd like to talk about how I stored this Dbpedia and Wikidata properties in my Neo4j database. First of all, we talked about that there are 1 billion or more relationships in these data sources. If we want to save these relationships all in one property or one node by creating a relationship for each node, this is a possible way. The most basic way, maybe, but this is possible. So then we will have 1 billion relationships, and this is a very big number, and our queries will be very slow. So I thought that it would be a good idea to group these properties into separate nodes according to the data source we retrieve them. So for Dbpedia, we call it Dbpedia property, and all the properties that are retrieved from Dbpedia belonging to some certain entity are stored in Dbpedia property node, and and other sources have their own names. In this case, another node for storing properties is Wikidata property. This yields in double the numbers of entities in our database. So this yields in a very low number of nodes in our database. What is the implication of this? When we actually have our user retrieve a specific entity in our database by simply clicking on the entity and reading its articles and searching through its semantic properties, it doesn't matter too much, because one entity can at most have 500 properties or something like that, and retrieving 500 properties and relationships from our database is not a big issue. But when we do batch operations, or when we try to implement a search function, this becomes a huge problem, because then we work on a big number of nodes, big number of entities. So every relationship of every entity we search is dealt within this search function. So if we are searching for a painting object, there are thousands of painting objects in the database. So if each painting object has 50 properties, then this will be a problem, because 50 times thousands of painting objects is a very big number. By using the second method, we greatly reduce runtime of queries, so that we only have 2 properties, 2 nodes for denoting properties in our database. So this greatly reduces the number of traverses through the graph. This is the storage of the semantic web, the Dbpedia and Wikidata sources in our database. Basically, this small adjustments is enough to store efficiently these node sources in our database. So secondly, I'd like to talk about how I approached storing entities under certain topics, categories, or subcategories. So as we talked about earlier, users can save entities or articles in their memory page, so that they can retrieve them later. We talked about that there are 3 layers of categories, which are called topic, category, and subcategory. Basically, there are 2 approaches to this. And the first approach is to store each entity under only specific topic, category, or subcategory. And the other approach is to store each entity when they are added to the below category elements, such as subcategory. We also store it in the topic or the above categories, so that when we try to retrieve these, we don't go into the below levels, but only retrieve from the topmost category, so that we reduce the access count of our query and make it more performant by compromising an aspect of structure and also a data replication in our database. So the advantage of the second method is, whenever we want to retrieve data from a top-level element, we don't need to access the category or subcategory that belongs to that topic. The disadvantage is, as we talked about, is data replication. The reason we should consider this option is if we have too many categories and subcategories and too many branches of this, then it would be a problem for us to retrieve these categories and subcategories performantly and retrieve also the entities below them. It will be non-performant. But in our case, this is not a problem because these categories and subcategories are only created by users, so there will be in a limited amount of these categories or topics, so this won't be a problem. So I went with the first approach where I only saved entities to the desired category. By this, I don't have the problem of data replication, and I have a more structured database, and also I don't have a performance problem because there will be no overflow of category or topic in our database because they are created by users. So basically, the main concerns regarding my application and design choices made throughout my experience was these two areas of how to store properties in the database and how to store entities in categories. As I told you, I approached it accordingly to my desired how I desire to retrieve the data from the database. I think this is a good idea to keep in mind that having some data replication might be a good option when you have too many branches or too many relationships. We can reduce the runtime of our query, but by replicating the data, but having narrow searches. So I'd like to give two examples of queries. The first query example is basically it is my approach that we only store entities in only the desired category. So the first query retrieves entities from topics. This is a query requests data from a subcategory. So the belowmost element, or the topmost element. This is a query that requests an entity from topic. So we want the entities under this topic, entities under categories belong to that topic, and subcategories belong to that categories that belongs to that specific topic. So basically there are three queries for that. And first we retrieve data from the topic, then we retrieve the categories under the topic and retrieve entities under those categories, and similarly it is applied to subcategory from topic to category going to lowmost elements. This is a much longer query than the other, but we have a structure of data and no data replication with this query. And the other query is simply the other approach where we store entities in topmost elements of categories also. So in this context, we only need to retrieve data from the topic because we know that under the topic, all entities are saved also. So I'd like to conclude by expressing the importance of structured knowledge and how we can make use of semantic web sources, resources to make use of and exploit the relationships between knowledge throughout the web. Actually, since the semantic web term is coined in the early 2000s, um, there is no much effort in using this in its original context. But I think through the growth of data, our needs also for structured data will never cease. And I think it's a good direction for Neo4j to go ahead, and because it's a great resource for knowledge graphs and graph databases. And I'd like to thank you finally and see any questions.